Hey everyone, welcome back to the channel for the first astronomy video that I'm doing. I took some time to think about what to do, and I think I figured out something. Some of my students in the past have struggled with just the scale of objects in the solar system, just how big they are, how big the solar system is, how big even the distance to stars are, or even the scale of the universe. So, if I tell you to think about the size of an ant, the size of a cat, the size of a dog, you can probably think about that really fast. But if I tell you to think about the distance of the Earth to the Sun, some of you may not know that off the top of your head. And for those of you that do, you might not be able to think about that scale in your head really fast. You just might know the numbers. For those of you that don't know, that distance is 150 million kilometers or 93 million miles. For a lot of my students, it took until we did a lab where we actually created a scale model of the solar system. And so that's what I'm going to do with you guys today. So the way that this works is we have to come up with a scale for the solar system to begin with, and it has to be a size that actually we can fit inside of the lab room that I'll be using. If you have access to a football field or something like that, that's better, but I don't have access to that. So this is going to be a very small scale, but you'll actually be quite surprised with the distances and the size of everything, even at this tiny of a scale that I'll be using. So for the scale that we'll be using, we'll be shrinking the sun all the way down to 3 millimeters in diameter. This may seem really small, but when we get to see the distances that everything is away, it'll make sense for why we're shrinking it down this much. So I'm going to go through with you guys how exactly we are going to calculate the size of all of the planets and then the distance to all of the planets from the sun. And after that's done, I'll actually make the model for you guys so you can actually see it. And it's honestly really cool in the very end. Okay, now to start with the math. So first we need to figure out what the actual scale is going to be, and I have the math here, and let me explain what to do. So like I said, we're going to have a scale diameter of 3 millimeters, and the way that we find the actual scale is using the actual diameter of the sun, which is about 1.4 million kilometers, and we divide the two. So I'm going to leave it in the units that they're actually in right now, and it'll make sense in a minute. So if you do 3 divided by this number, you get it equals 2.154 times 10 to the negative 6 millimeters per kilometer. So this might look weird to those of you that have done something like this in the past. This may look weird to you just because it's 2 different units for measurement, but this will make sense in a minute. For those of you that aren't good with scientific notation or have not seen it before, I decided to put it here in decimal places. So if you want to follow along and do the calculations yourself and you have a calculator, or if you want to use a calculator on your computer or phone, you can, and you'll see how we do this. So I have here a table that we're going to fill out that is the diameter for all of the bodies that when we have everything scaled, and also the semi-major axis for everything once it's scaled. I'll explain what a semi-major axis is when we get to it, but know that for the sun it's going to be equal to 0, so I just have that marked out. So starting with Mercury, we have the actual diameter is 4,879 kilometers. And to do the math for this and get the actual scale, we do the 2.154 times 10 to the negative 6 millimeters per kilometer times 4,879 kilometers. And this is why I left it in millimeters per kilometer. When you do the math, the kilometers cancel out because you have a kilometer on the numerator and a kilometer on the denominator. So you're left with millimeters in the end. So Mercury, when it is scaled down, when we have the scale factor of 2.154 times 10 to the negative 6, it makes it all the way down to 0.011 millimeters, which is absolutely tiny. Next up is Venus, which is our sister planet, because the diameter is very similar to Earth's at 12,104 kilometers. So again, we just multiply the 12,104 kilometers by 2.154 times 10 to the negative 6 millimeters per kilometer. The kilometers cancel out, and you're left with 0.026 millimeters for it. So a little more than double that of Mercury. And next comes Earth with a diameter of 12,756 kilometers. So when you do the math for this and you cancel out the kilometers, you're left with 0.027 millimeters. So very close to the diameter of Venus, like I said before. Mars comes next, and it's the final of the rocky planets with a diameter of 6,792 kilometers. Multiplying by the scale factor and canceling out the kilometers, you're left with 0.015 millimeters. So a little closer to the size of Mercury than it is the size of Earth or Venus. Next up comes the first of the gas giants, with the largest planet in our solar system being Jupiter. Its diameter is a lot larger than any of the rocky planets, with a diameter of 142,984 kilometers. When you multiply this by the scale factor, you get a diameter of 0.31 millimeters. So even though the diameter may look huge, when you scale it down, it is still tiny compared to the sun of 3 millimeters. Saturn is the second largest and everyone's favorite to look at through a telescope because of looking at the rings. It has a diameter of 120,536 kilometers. This is just under 10 times the size of the Earth. And when you do the math for this, you're left with 0.26 millimeters. Up next are the ice giants, the first of which everyone laughs at, being Uranus, or the correct pronunciation being Uranus, but I will still smile and laugh at all of the Uranus jokes. It has a diameter of 51,118 kilometers, and you do the math and cancel out the kilometers, you're left with 0.11 millimeters. And last but not least comes Neptune with a diameter of 49,528 kilometers. When you do the math for this one, you get 0.107 millimeters. I did 3 decimal places for this one compared to 2 for the rest, just so you could see that it is a different size from Uranus. So now we have all the calculated values for the diameter of the planets and the sun. And as you can see, the planets are tiny compared to the sun. For a size comparison, grains of sand are between 0.1 and 2 millimeters. So 6 of the 8 planets are smaller than the smallest grain of sand in this scale. See if you can find the smallest one in this picture. Now divide that by 10, and you get the size of Mercury in this scale. Up next, we need to find the distance to each of the planets from the sun, so we're going to be looking at the orbits. And I have this image here just to show you guys that orbits are actually elliptical and not perfectly circular. So the 2 different axes on here, being the major and the minor axis, we'll be using the major axis for this because when you draw out orbits, the major axis goes through the focal points of an ellipse, and for orbits, the sun is at one of the focal points. You won't really see orbits this elliptical unless you're looking at comets or asteroids, because most of the planets are nearly perfectly circular. Mercury's orbit is a little more elliptical, but still very circular. All right, so for part 2 of this, we'll go in order again, starting with Mercury. And this is where the numbers get a lot bigger, and this is where you'll see why I made the scale the way I did. So Mercury has a semi-major axis of 58 million kilometers. The scaled orbital radius with this is 125 millimeters, and I'm changing this into meters just because it makes it easier in the end. So it has a semi-major axis of 0.125 meters. Venus is next with a semi-major axis of 108 million kilometers. So when you multiply this by the scale factor, you get 233 millimeters, or 0.233 meters. The Earth is up next with a semi-major axis of 150 million kilometers, like I said earlier. Multiply this by the scale factor, and you get 323 millimeters, or 0.323 meters. Mars rounds out the inner solar system with a semi-major axis of 228 million kilometers. Doing the math for this, you get 491 millimeters, or 0.491 meters. So you may be thinking that we're halfway there and we're only at about half a meter. Why did I make the scale like this? With the gas giants and the ice giants, you'll understand why. So as you can see here with Jupiter, the semi-major axis is more than 3 times further than Mars, with a semi-major axis of 778 million kilometers. And when you do the math for this, you get 1.976 meters. So do you guys see why I made the scale the way I did?
Hey guys, editor's note. I realized that I accidentally wrote down the wrong value for Jupiter. When I did the math, I did it correctly, but for some reason I put it as 1,976 when it was supposed to be 1,676. So I have it corrected here. I did not realize this until I was done recording everything, so ignore that I messed up at first.
Saturn comes next, and the semi-major axis again nearly doubles compared to Jupiter. And for this one, you get a semi-major axis for Saturn of 3.084 meters, with Uranus with a semi-major axis of 2.8 million kilometers. You get a scaled semi-major axis of 6.176 meters. So now we're starting to get a lot larger of a semi-major axis, and this is why you need either a large room, or if you make the scale even bigger, then you're going to need to go outside and have a big field. A football field works very well if any of you want to try this in the future. And finally, we get to Neptune with a semi-major axis of 4.5 million kilometers. This is where you really see how big the solar system is. Doing the scale factor for Neptune, you get 9.725 meters. And now we have all of the calculated values we need. So as you can see, the diameters for each of the bodies is the size of a grain of sand or smaller, but the semi-major axes go almost all the way up to 10 meters. For a size comparison for the semi-major axis, telephone poles are about 11 meters tall, so if you look outside and there's a telephone pole near you, this scale is going to be almost all the way up the telephone pole. Okay, now that we have all of the numbers we need, it's time to actually go and set it up. So let me go through the equipment we need, and then I'll show you everything for setting it all up.
Alright guys, so unfortunately I was not able to use audio from the videos I took while I was setting up the experiment because there was some noise in the background that the audio picked up, and it's very annoying. So I'll just talk over the videos from here rather than you guys having to listen to a loud beeping sound the entire time. For the equipment, what you're going to need are 10 meter sticks, some string, and some pins. Okay, the first step in this is setting up a pin for the sun at one end of the room, and then moving the string all the way down to the very end, making sure it's in a straight line, and then putting a pin in at the end to hold it in place. The second step in this is setting up the 10-meter sticks, going all the way down the room, trying to keep it as close to the string as you can, just so the measurements are accurate. Okay, now you choose which pins you want to use for this. I decided to color code them slightly just because I felt like it. You don't have to do that, but if you want to, you can. Now is when we start placing the pins. Of course, these don't really equate to the scale of the size that we calculated for them, just because they're smaller than a grain of sand, and I can't think of anything that we can place down for that. So instead, we'll just use these pins. Starting with Mercury, we calculated that it would be 0.125 meters away, which equates to its semi-major axis of 58 million kilometers, and you can see here that it's very close to the Sun for this scale. The second planet is Venus, and we calculated that that was 0.233 meters away, and the semi-major axis in reality is 108 million kilometers. So you can see it's a little further away from the Sun in this scale, but still very close. And then next up we have us at 0.323 meters away, and the semi-major axis in reality is 150 million kilometers. So we're starting to move a little further away, but still with our scale, the inner solar system is very close to the Sun, but you'll see in a little bit why I made it this way. For the last planet of the inner solar system, we have Mars at 0.491 meters away. So the inner solar system at this scale is less than half a meter from the Sun. This equates to the semi-major axis of 228 million kilometers. Here's an image from a top-down view of what the inner solar system would look like if we were in a spaceship and flying by the solar system. Next comes Jupiter, which is supposed to be at 1.676 meters away, but I didn't realize my mistake until after recording everything. The number now is correct, but the image is not, so just move it about 30 centimeters closer. So the semi-major axis in reality is 778 million kilometers. So if you do the numbers correctly, you should get 1.676 meters away. Okay, next up is Saturn, where we have a calculated distance of 3.084 meters. As you can see, it's really far away from the Sun now because it won't even have the Sun in focus with Saturn in focus at the same time. And this is due to the fact that in reality, it is 1.432 billion meters away. At this distance, the Sun, I believe, just looks like another star, but a bright star. Now we're getting close to the end of the solar system with the first of the ice giants, Uranus, which we calculated to have a distance of 6.176 meters, and we have the actual distance being 2.867 billion meters away from the Sun, and this is just a little over double Saturn's distance. And the Sun is definitely just looking like a regular star at this distance. And finally, we get to the very last of our planets with Neptune at 9.725 meters away from the Sun. As you can see from our model, we can barely see the Sun with our picture. In reality, if we were this far away and looking at the Sun, it would be even dimmer than it was at Uranus, and it is looking just like your average star. and its actual distance away is 4.515 billion meters from the sun. Okay, I also took a video going from the sun all the way out so you guys can see what it looks like. You can see just how big of a jump it is between the planets of the outer solar system.
And that's how you make a scale model of the solar system. I hope this helped you guys see just how big the solar system is in reality and see just how small we are in reality. And I wanted to do a couple more numbers just to show you guys that even though the solar system is really big, the universe is even bigger. Because I did the math for Voyagers 1 and 2 and our closest star just to see where they would be on this scale. Of course, all of them would be outside the room. Voyager 2, which is the closest of those three, is at 20.3 billion kilometers away, and on this scale, it would be 43.7 meters. Voyager 1 is 24.3 billion kilometers away, and this equates to 52.3 meters in our scale. And then Proxima Centauri is the furthest away, and this is a crazy number. So it is 40.1 trillion kilometers away, which is 4.24 light years. And this equates to 86.37 kilometers away, or 53.67 miles. So think about how far a drive that would be from your house or your apartment, and that's how far away the closest star is when you have a scale multiplying by 2.154 times 10 to the negative 6. That's how big the distance is between us and the closest star, which is crazy to think about. And numbers get even bigger from there, but I won't calculate those with this scale. You can calculate those numbers yourself if you want, and you'll just be amazed how big the universe is. So that's it for this video. Make sure to like and subscribe, and leave a comment if you want. I'm always looking for ideas for new videos since I don't have access to the curriculum yet, so I'm willing to do anything. And I have one video in the works right now, so leave a comment and I'll try to get a video out with that topic. See you guys next time.